I'm ready to record. All right, so here we go. Now, this is the same thing with the salt bridge again. And what they've done on this diagram is they've put in a voltmeter. Check the airflow. I'm going to have to do that. Remind me at lunchtime to check the airflow, guys. All right.
I think it's about to blow up.
Where was I? Okay, so what they've done here, they just added a few extra little pieces in here. What they talk about is measuring the voltage going across this wire. Now, if you take a regular voltage meter and you do that, the thing about energy, we go back to Gibbs free energy again. Gibbs free energy says that when an electron flows through a wire, it creates friction. That friction is going to reduce the flow of electrons, and we're losing energy. So the number you get in here is not going to be that accurate. What they're doing now is they're using potentiometers, which is a little bit more accurate system, but with the new digital voltmeters, they're even better than all of the rest of them. So when you get a number here, it's pretty close to what the actual number is. It's compensating for it. If you take a regular voltmeter and hook it up, the voltmeter is actually going to draw electrons through it. That electron is going to create heat. That heat is lost in the energy. So it's not a true reading of what you get.
So would it be more accurate if you put it closer to the source of electrons in a circuit?
If you shorten the wire between the two chambers, is that what you're saying?
No, I mean like if say you're measuring a galvanic cell, if you put it closer to the anode, like if you actually
No, it doesn't matter whether it's close to the anode or close to, because it's a complete circuit.
Okay.
So that wouldn't really make that much difference.
Are we saying,
Or let me put it this way, it wouldn't have a noticeable difference in the number on the voltmeter. Yeah.
so are we saying we're losing electrons somewhere between there, or what's
No, the electrons are converting into heat, and the heat's being dissipated, and that's lowering the amount of energy, and that's a measurement of energy.
So yes,
This is called volts. We're going to get to it, but it's called volts, which is equal to joules per coulomb, and joules is energy. So we're losing energy. That's part of the free energy that we're not having. Bobby?
When you lick a battery, is that feeling you get electrons jumping to your thumb?
What? I didn't know
Not
this.
whole battery, you can't say.
Is that a thing?
Yes.
You've never licked a battery?
No,
Don't.
never looked at that.
Don't.
It's in the
All right.
science that you have to do with 9 volts to see if it
Moving
works.
on.
Supposedly. Smart thing.
All right, Zach.
Sounds smart.
So
Your face.
electrons are going to flow from cathode to anode. That's the key phrase in this one. And I've already talked about if I hook this thing up without the salt bridge in it, it's going to have a real quick burst of energy, and then it's going to stop. So that's the message on this particular slide. Now we're going to look at the salt bridge, and the salt bridge is, like I said, usually a glass tube, and they put some kind of solution in there that's going to allow the flow of anions and cations. When I read the book and I looked at the slide, they had a kind of, it almost sounded like this little zinc cation is going to go over here. Okay? It's not. The cation is going to move toward the cathode, but it's not going to go to the cathode. And that's what the salt bridge is in here for. So I've got a zinc +2. Well, I've got a nitrate anion in here, and that is going to neutralize it. And that's going to bring the negative charge over this way. It's going to bring the positive charge over this way. So our charges are going to be balanced out, which means the circuit is going to keep flowing, which means it's going to continue to produce electrons and continue to have a measurement on the voltmeter. That's the whole purpose of the salt bridge. So the cation is going to move that way, but it's going to get kind of captured, if you want to think about it that way, in the salt bridge. The anion is going to move this way, and it's going to be kind of captured in the salt bridge. But that takes that extra buildup of negative ions here and the extra buildup of positive ions here out of the picture, and therefore the electrons are still going to be generated and flowing. And that's the whole purpose for the salt bridge. And this is repeating basically the same thing. Electrons are going to flow from anode to cathode. And what they have done here is they're showing this would be the anode, and the anode, the electrons that are on part of that anode are going to be the electrons that are flowing. That is also going to produce the cation on that particular side, and that cation is going to cause this particular anode to get smaller and smaller and smaller, losing mass, because there's part of the mass right there. On the other side, the cathode is going to grab those electrons, and the picture really is not really clear here, but it's actually going to bring that metal onto that cathode. It's going to plate on there. And we'll talk about that in a little bit. And what do we have next? Am I going backwards? I don't think so. Okay, so it's repeating the same thing I've already said. Electrons are taken by the cation, neutral metal is deposited on the cathode, so your deposition, your cathode is going to increase in mass because those neutral, those metals that are going to be produced over, in this case it's copper. Copper metal is going to be plated out onto the copper electrode. Now we're going to look at electromotive force. Electromotive force is basically that electron, and we're measuring it. So if you look back at that slide right, get back to it here. Come on. Right here, that's a measurement of electromotive force. Electromotive force is the force generated by those electrons flowing through that wire. And it depends on the kinds of cations and anions, or the different types of reduction reaction potential metals that you put into the system is going to determine how much voltage you're going to get. So the whole thing that Kim and Audrey and Lydia are trying to work on is to figure out how can I get the maximum amount of electricity out of a battery. And they're still working on that. Come a long ways now. You can actually get batteries by running a certain type of paper through a printer. You can print a battery. They're getting real close to that being commercial products. They're supposed to have released it this year, but I don't know where they are.
That is really cool.
But the what?
So that's really cool.
Bless you.
So you need a new battery for your iPhone or something like that. You just print it off on the printer and hook your iPhone into it and it runs. That'd be so cool.
3D printers are the most
Bless you.
amazing things on the
Okay.
planet.
But anyway, the electromotive force is always going to flow from higher to lower potential. So it's the potential, which we call the cell potential. That's the direction of the flow for electromotive force. And that translates into the same thing, where it's going to flow from the anode to the cathode. So you got very high potential force here, it's going to flow down here. So another way of saying that exact same thing, the electricity is going to flow from the negative pole to the positive pole. Same thing. Okay? Has to flow that way. If you ever take your calculator and put the batteries in backwards, it doesn't work because it's trying to flow in the wrong direction. All right. So electromotive force. Let's see if my E's didn't come out. Doggone it. Went too far. All right, go back. Electromotive force is the potential between the cathode and anode. That's the definition of electromotive force. It's how many electrons is going to be moving through there. If you want to put a voltmeter on there, you're measuring that. We also call that same thing the cell potential. And they use, I used, I think later on you're going to see that E changes. But if you look in the textbook, that E is really strange. I don't know why they do it. I had to figure out how to write this thing. So it kind of looks like a real crazy looking cursive E.
That's way too
If you
complicated.
ever see that symbol, that is electromotive force, that's the cell potential. And if you see that, then what you're seeing down here, that's the electromotive force for the cell, which would be the whole galvanic cell. Okay? And I was searching last night trying to figure out how to make it look like that, and I think I was halfway successful, but it was a pain.
Can you move second drive? Gracias.
And so if you have your textbook open, you can see that crazy looking symbol on page 795. So they're talking about the electromotive, and it's all the way through from there on out. Every time you see that, you're going to see that crazy looking little E.
Don't knock
And
me.
it depends on how fancy you get, you can make it all kinds of fancy. But basically, we measure the electromotive force or the cell potential in volts. And volts are translated directly into joules per coulomb. Coulomb, I don't know if you guys remember doing the virtual chemistry lab on, I don't think it was Rutherford. I don't think it was Thompson.
Is that Warren?
What was the other one?
Millikan?
Was it the Millikan oil drop experiment where you had to calculate the, yeah,
Yes.
because you were using the
Yes.
charge of the electron to calculate the
Oh,
mass of the
God,
electron.
That's awful.
That's a long time ago.
I
Yeah.
hate
Long
that.
time ago.
That would take
And the math on that was kind of tricky.
It took forever.
Yeah.
Is that a one?
myself to do that.
So, yeah, it's one. 1 volt equals 1 coulomb, a joule per coulomb, and use abbreviation JC. So an electron, and you figure this out in the Millikan oil lab, has a charge of 1.6 times 10 to the negative 19 coulombs. C stands for coulombs. My zero didn't get superscripted there. It's supposed to be 25 degrees Celsius. So they're going to use, and I tried it here, it didn't work too well, but they're going to use that little O as a superscript. It's kind of like the degree symbol. That means standard conditions. That means 1 atmosphere. That means 1 mole, 1 molar concentration. That means 25 degrees Celsius. So they're talking about standard cell potential. Okay. You ready? No. And this is where it's going to be really easy, writing redox equations, doing half reactions, because this table is given to you. This is redox reactions. This is, the title of it is Standard Reduction Potential. So when they're writing these little half reactions right here, they're telling you this is what happens when this particular cell is part of a galvanic or a voltaic cell. This is how much electricity or how many volts it's going to produce.
Would that be if it's the anode? Sorry.
Anode, no,
Why?
because where does reduction take place?
Yeah.
Red cat,
Cathode.
cathode.
Okay.
Okay, this is on the cathode. However, if you take that thing right there, you flip it, guess what you got?
Yeah.
You got the anode.
Okay. And
So-
so do we have to? Don't the electrons always come from the anode?
They're going to flow from anode to cathode.
So
So
Do we always flip it?
we're going to do a little math with that.
Okay.
You see it down the road already, yeah?
sorry.
That's okay, that's fine, that's fine. All right, so here's that table. They're called reduction potentials. So if I'm looking at, this is a reduction potential, so fluorine gas is being reduced to fluorine ion. It's losing, reducing, it's gaining electrons, GER. So these are gaining electrons, so we got a negative charge right there. And this table, you got another one in your textbook on page 796. This table is what you're given in the test. And it's set up in order of increasing voltage. So you look down here, here's lithium. That's the reason I asked what the lithium ion battery contains, because lithium is one of the two elements in a lithium-ion battery. And wasn't that the battery in the 787 that was giving them all kinds of headaches?
Yeah.
It's a lithium-ion battery.
It's what's in
I'd be
everything
curious
now.
to know what the other part of that reaction is, to know why it's keying. So, but you know, lithium has a potential of a negative 3.05. It's one of the most negative ones of all these different elements. They're set up like that on purpose, and the whole thing is based around hydrogen.
What does it mean if voltage is negative?
We'll get to that.
Okay, sorry.
It's just like,
Stop skipping ahead, Alexis.
I'll just stop asking questions. 'cause
No, no,
clearly
don't
you're just
stop
gonna-
asking
Clearly you're just
questions.
gonna get there the next slide.
I hope we're gonna get there, all right? All right, so that's the, I don't think that's all. Yeah, there's more to it. One more? There we go, okay. So, to get these numbers, they standardize everything, and it's all based on hydrogen. So what they do for hydrogen, and this is only half of the reaction wells, this would be one well over here and the other well's over here. What they're doing is they have this device where they put in hydrogen gas at 1 atmosphere. So they put the hydrogen gas in there. Well, the only place that hydrogen gas can go is to go down here. You have a platinum electrode, and that platinum electrode is surrounded by hydrogen cations in the system. So what does that make this electrode? Anode or cathode?
I'm sorry, what?
Oh, cathode.
Makes it the cathode, right? Because you got the hydrogen ions produced over here. So this is the cathode side. Now, take any of the other metals on this table and create them on the other side of this galvanic cell as the anode. Put the little instrument up there and measure the voltage going across, and that will give you the voltage for that particular metal. And that's how they come up with this table. They arbitrarily say, we're going to base everything on oxygen, and oxygen is going to give us,
You mean hydrogen?
hydrogen. Hydrogen is going to give us the zero value. So it's arbitrarily set up, the zero value, and everything is based on that. Now, if we use a metal and we don't get a flow of electrons, or we get a reverse flow of electrons, we're going to get the negative voltage.
Can it do that?
Well, not actually, but theoretically we can do that.
Well, if it's theoretical, why is it on the table as being negative correctly?
Because these are arranged in order of
Activities here.
Decreasing voltage.
reduction potentials. The highest one is listed at the top, the lowest one is listed in the bottom.
Oh, yeah, but.
And the one that's listed above the other one is always going to be the reduction potential. So if you're looking at this, and I'm just gonna take two metals at random thing. I'm gonna take silver here, and I'm gonna take magnesium down here. So the one on top is gonna be the reduction.
So it's gonna be the
The
cathode.
It's gonna be the cathode. The one down here, I reverse it, and it's gonna be the anode.
Makes sense.
You have to reverse it?
Yeah, because the anode is gonna be where the oxidation occurs, and so it's gonna lose electrons. This one up here is gonna gain electrons.
So with that,
So the flow of electrons are gonna go from this one to this one. Flow of electrons are always going up.
would reversing it make its potential positive? Or does that affect that at all?
No, that does not affect it.
Okay.
Real good question.
Mr. Leather.
Okay? Yeah.
So if you took like lithium and whatever the highest one on that list is,
Fluorine?
yes, and you put them in a galvanic cell, and you measured the voltage, would that be the potential of the cell?
Yeah. Yep.
Okay.
Does
So
fluorine,
the one that would produce the greatest would be like lithium and fluorine. Okay.
are there reduction potentials related in any way to like their electronegativity or anything like that? Or just happens to be like?
I don't know, I had to think about that one.
Okay.
So, Tyler just opened the door up to a wonderful equation. So here's the equation.
Thank you, Tyler.
Okay? So the potential of the cell is going to be whatever the potential is for the cathode minus whatever potential is for the anode.
Oh boy.
All right? Now, if I look at this paper and we're looking at fluorine in the form of a gas plus 2 electrons is going to produce 2 fluorine anions, and we have an E voltage for this particular process of 2.87 volts. All right? Now, that's at the very, very top. If we go to the bottom of that table, we have lithium, which has a +1, plus an electron is going to give us lithium in the form of the solid, and the voltage here is a -3.05. All right? Now, which one of these is going to be the cathode, which is going to be the anode?
The fluorine would be the cathode,
Okay, so this is the cathode,
and the lithium would be the anode.
and this is the anode. Okay? Now, if we take that particular equation, the E for the cell is going to be equal to the potential for the cathode. Well, that is 2.87 volts. And then we're going to subtract from that the potential for the anode, which is a -3.05.
So,
So the potential of this cell is what?
5.8,
Lots of voltage. So a lithium, you know, and here's the trick, is how do I get that as my cathode? Because it only exists as a gas. So the problem is going to be coming up with a way of getting that in the form of a cathode where I have that solution and the cathode to make that work. But it's going to produce a whole lot.
so does that mean we can basically tell in a reaction which one's gonna reduce and which one's gonna oxidize just by having that table?
Yeah. These are all reductions, every one of them.
I really think, okay.
Every one of these is a reduction.
But if you had like 2 on the same list, and you just went with which one was higher, that's gonna be the one that reduces. and
That's
the
going to
one
be the
that flip.
reduction. So the reduction is always the higher of the two.
Okay. You
Okay.
Probably.
Now, we could do this,
What we're doing with gas.
but what we're going to have to do is we're going to have to take that fluorine and we're going to have to get it down toward solid phase, which is getting down toward absolute zero.
What? Yeah, because
In
you
order
can't-
to make this a
right.
cathode, we're going to have a solid.
Right,
We can't do a
You
gas.
can't have a gas.
So we got to cool this down really, really, really well, and then we'll get a really good battery.
Wait.
But of course, the battery's going to be
Really
expensive because you got to
cold.
pay for. Yeah, it's going to be cold and it's going to be expensive.
Is that why sticking your batteries in the freezer
What?
basically helps?
I don't know that that really has anything to do with it. I do know that when you do put batteries in the freezer, they're supposed to last longer because batteries generate heat, and heat is going to wear the battery out in the long run. So if you have batteries that, you know, they're not being used, you put them in the freezer, they're not going to have generate any heat.
Why do they get standard reduction potential for fluorine if it's at,
That I don't know.
if it's at standard
question.
temperature? If they'd have to cool it down to even do that?
Yeah, I really don't know the answer to that.
Okay.
You're just giving me all kinds of questions I don't know the answer to.
I'm sorry.
That's okay.
What you do is you
Hey.
gas.
I like
No, you
questions
take a
I don't know
phone
the
number,
answers to
yeah.
because it makes me think and makes me go look for answers. Okay, so we're looking at the standard cell potential. You guys remember the extensive and intensive properties of matter?
Kind of, not really.
An extensive property depends upon how much you have, how much mass you have, how much volume you have. Well, cell potential doesn't matter about that. It doesn't have a thing to do with it. It's an intensive property. So the charge is not going to be affected by having a larger or more massive material to actually work. So we now know how to figure those out. So here's a sample problem for the oxidation of zinc. We have the electron, the reduction potential for that one, or the electromagnetic force for zinc, is a negative 76 volts. What is the E naught for the cathode in this particular problem? So what I did is I took that formula, and I know the E of the cell because I can read it right here off of the voltmeter. And knowing the E of the cell, I can then plug in the E for the anode and calculate the E for the cathode. Straightforward calculation. So that's a sample of the problem. And we're going to stop right there.